Okay, for this session, I think we will do something more interactive. So according to Datacop, if it's okay for you, we can, if anybody has any question at any time, just put up your hand and I will try to come there and try to answer your questions.
Yeah, sure.
So you will introduce by yourself. So good luck. Thank you.
Okay, thanks. I hope I can just set up this. Okay, I'm sorry. Obviously there's only. Okay. It's the wrong window. The wrong. Okay. Yeah, I know. Sorry.
Are there any questions so far?
Okay, I don't know why he's insisting to use my second screen.
Use it
Okay.
that way.
I'll just use it this way. And I haven't got it on my screen, so I have to look at the presentation or at the beamer. I'm sorry. And I'm sorry for the interrupt. Okay. There's also a screen. Thanks. My name is Clemens Hopfer. I'm from Vienna. I made my amateur radio license in 2010. And in 2006, I started at the Funkfeuer Community Wireless Network. And since then, I've been interested in wireless communications, high-frequency engineering, and of course, digital modulations and communications. And I'm studying at the Viennese Technical University, electrical engineering. And so I thought, because there is not that much wireless hacking or stuff at the physical layers at the Congress, I thought maybe an introduction in basic wireless stuff, digital stuff would be interesting. And let's start with the table of contents. I've basically divided this in a few parts. In wireless basics, modulations, how we actually do analog. Although we are doing digital radio communications, we still have to do analog stuff. Channel coding, so forward error correction and so on, and a bit of channel access. And the first I start with is the Shannon communications model, which is basically consisting of a source, a transmitter, or encoder, and the channel and the receiver and the sink where you actually want to transmit your information. So that's what you at least need to have wireless communications or any kind of communications. And the channel is something very abstract. So you can have a wireless channel, you can transmit over basically any medium, and you will always or almost always have noise, different kind of noise, and interference coming from other people, other devices, even if from yourself. And you have to make sure that your encoder and your decoder can actually make the most of your channel so you can transmit your data. A bit about wireless channels. So wireless channels are very unreliable. You can, in very small ways, like predict it, but it's still very noisy. You can have interruptions or like interference, and for mobile wireless channels, it's even worse because you can because of the movement of the different stations. You have interference between your own station, parts of like buildings around you, which are basically reflecting your signal and interfering with the signal you actually want to receive, and because of different time diffractions between the sending and the receiving time. So yeah, okay, sorry. We have a digital communications model, which is used when we do digital stuff. So we have a source like before. We have a source coder, which is, for example, an MPEG coder or any kind of audio codec, GSM codec, which does data compression and tries to minimize your data. And then we have a channel coder, which tries to add redundancy again. So your receiver has, or it's easier for a receiver to receive a signal and to make most of your channel. Then we have got the modulator line coder, where we are actually transmitting the signal and sending it to a radio channel. And on the receiving part, it's the same thing, just the other way around. And what I'm going to talk about is the channel coder and modulations and a bit of wireless channels or wireless stuff. First of all, when we speak about wireless spectrum, what do we actually mean? And I found this great XKCD slide, which shows this pretty good. We are using this part of the electromagnetic spectrum, so from 3 megahertz to 300 gigahertz. Of course, most of the communication isn't done in this spectrum because 3 megahertz is shortwave radio, where you're only transmitting very narrow band signals and use usually huge antennas to get like a few hundred kilometers or 1,000 kilometers. And at the upper end, we've got really high frequencies where it's actually extremely hard to build devices for this. So, for example, radar devices are in this area, or even or a bit lower. But most of it is done between like 100 megahertz and 30 to 60 gigahertz. A few examples. We all know Wi-Fi, which is at 2.4 and 5 gigahertz bands, which are ISM bands, and these spectrum bands are actually free for use. So you still have to have a license for your device, but the license is on the device itself. But you can freely use it for any Wi-Fi access point you want to do, and it's for industrial, scientific, and medical stuff. That's what the abbreviation stands for. We are also using here DECT, which is in the upper side of the GSM band, and it's using 1.8 to 1.9 gigahertz approximately. UMTS is at 2.1 gigahertz, and LTE is in Europe using these 4 frequency bands, but these 3 are actually GSM bands and are converted to LTEs, and 2.6 gigahertz is the frequency band which is actually at the moment mostly used for LTE. And 433 and 868 megahertz are small free bands which are also ISM and SRD for short range devices, which are also free to use for like weather stations, telemetry data, or part of smart meters are actually using this. And what you usually buy when you get an RF module for your Arduino is in this frequency bands, as long as it's not 2.4 gigahertz. When we come to wireless bandwidth, there's one main rule in telecommunications. Transmitted information always has a bandwidth. If you have a signal that has no bandwidth, you can't transmit information. So this also means the faster you transmit information, the higher your bandwidth will be. And if you look at the Wi-Fi, the new Wi-Fi specifications, you will always see that the new specifications have bigger channel bandwidth, and so they can transmit faster. And a short thing about wireless channels, there are actually 2 definitions of channels, telecommunications. The first one is the transmission channel, where we actually have a physical channel where the information gets transmitted, and the logical channel, which is is more or less a standardized frequency for your transmission system. So your Wi-Fi has got specified channels, and you don't need to enter your exact frequency. And these are specified to have optimal spectrum usage. One of the most important theorems in telecommunications is the Shannon-Hartley theorem, which tells the upper limit of information rate you can actually transmit over a channel if you have only one transmitter and one receiver. So this is, even if you have perfect error correction, you can't get over this limit. Although in wireless communications we can have multiple transmitters and multiple receivers, which we actually use when we do MIMO stuff like LTE or the Wi-Fi N standard. This is sort of an exploit. This theorem is basically thought for cables and is not defined for channels where a channel changes and where a few centimeters of spacing of antennas is completely different in the sense of a channel. And this is this formula where we have got C, the channel bandwidth in bits per second, B is our signal bandwidth in hertz, and the binary logarithm of 1 plus SNR, where SNR is the signal to noise ratio. In telecommunications, we always speak about signal to noise ratios, so independent of how high your noise actually is, you always know how good your quality of your receiving signal is if you have got the signal to noise ratio. And this is specified for noisy channels for additive white Gaussian noise, which is more or less the worst case of noise you can have because it's completely unpredictable. Digital signal processing is done in baseband signals usually. So if you've got an analog signal, you usually have intermediate frequency, which is about, depends on the signal, depends on your receiver or transmitter, is about a few hundred kilohertz or megahertz. And in digital systems, we use a 0 hertz intermediate frequency, which is complex because computers can easily calculate with complex signals, and when we get to modulations, it will be a bit clearer. When we center this at 0 hertz, we of course have the left part, which are actually negative frequencies, which is a bit odd, but if you think about a channel where we have got a frequency here and the starting and end frequency here, you still have the left part of the channel. So if we generate a complex representation of the signal, we still have the negative and positive parts of the frequency, or of the frequencies of the whole channel. This is a typical receiver of a software-defined radio, a system which is just the bandpass filter at the front or after the antenna. Then you've got the low noise amplifier, which is a really good amplifier, which amplifies your received signal and adds every amplifier adds noise, and this amplifier has very low noise. And then you've got two mixers, which are locked over the same local oscillator, but with a different phase offset and with 0 degrees phase offset and 90 degrees phase offset. So we generate our real part of the complex representation and our imaginary part of the complex representation. And after this, we already have the analog digital converters, which just convert your analog signal into digital and then do digital signal processing. And because we do all signal processing and most of the filtering in software, it's very easy to adapt digital wireless communication systems. So, for example, your Wi-Fi or your phone, the baseband chip of your phone usually can transmit or receive different modulations or a lot of different types of telecommunication standards like GSM, a lot can also do UMTS and LTE in the same baseband chip. And this is because the signal processing is all done in software, and if you have a new signal standard, you basically just do a firmware update. And the other way around, if you want to send signals, if you want to modulate signals, it's just you have your signal processor, your digital analog converter, and again mixers which do up converting to your destinated frequency, and then your power amplifier. So it's the same setup, just the other way around. Then about baseband modulation, the first question is, why do we actually modulate data? We could just send rectangular impulses over our Wi-Fi channel or our wireless channel, but rectangular pulses have very high bandwidth and are very inefficient. So they would just use most of the spectrum, and you would need a lot of power, or you can actually not that easily transmit rectangular pulses. You always have to modulate them. And what we also want to do is to match the channel characteristics. So if we have got a noisy channel and a small signal to noise ratio, we want to use a modulation that is more robust for this noise. And if we have a very good channel, for example, if your Wi-Fi access point is just a few meters apart from your laptop, you can use modulations which are high in bandwidth and which just has a lot of throughput. There are a few modulations I picked which are mostly used. The first one is ASK, amplitude shift keying. I haven't got a slide for this because it's actually quite easy. You just take one or two amplitude levels and just modulate it with your amplitude. So if you have only got one, you're basically doing on-off keying. So if you've got a signal, you, for example, receive a 1, and if you have got no signal, you, for example, receive a 0. Frequency shift keying is doing something similar, just with two frequencies, and is a bit similar to FM modulation, analog FM modulation. We have two frequencies, and do modulating on depending on what we actually want to send with two frequencies. Then we've got phase shift keying, which is a phase modulation and is commonly used. This is BPSK, binary phase shift keying, which is the easiest form. We have the Gaussian complex I only know the German word. It's the German. It's even the complex plane. Yeah. So, thanks. We've got the Gaussian complex plane, and we've got two symbols here. And these are spaced 180 degrees apart, so we have got a positive symbol and a negative symbol. And with this modulation, we have got a wireless bandwidth of about the symbol rate we actually use, and we can transmit 1 bit per symbol. If we enhance this, we have a QPSK, where we have got 4 symbols, which is actually not much different than this. It's just BPSK in orthogonal or spaced 90 degrees apart. And with each symbol, we can transmit 2 bits. And the nice thing about this is it has got the same bandwidth as BPSK and the same error probability. So it's usually more efficient to use QPSK because you don't need more power and you have got the same signal. You only need the same signal levels at the receiving part. And this is because these are 2 pairs of symbols which are orthogonal. Then we have got MPSK. We can just add more symbols, which means that the spacing between the symbols gets lower. So we need more power of the signal at the receiving end to transmit this or to have lower or low errors, a low error rate. The next thing is quadrature amplitude modulation, which is a combination of amplitude and phase modulation, and it's just the symbols in grid arrangement. And you can have any size of grid. For example, you can have 265, 56, or any number of symbols you want to have. And with each symbol, you transmit, in this case, It's 4 bits, so it's 16 QAM. Then we come to channel coding. What we usually want to do is, if we've got our binary stream which we want to transmit, this stream is can have like lot zeros or a large number of ones after another, and we want to have basically a random data stream. We don't want to have unmodulated signals. And for this, we are using usually a pseudo-random sequence. And this is, for example, the generator for DVBS, which is a 15 bits linear feedback shifting register. And the output is here, and it just gets XORed with your input stream. And the receiver also needs to know this, so he can actually then unscramble the received bit stream. Due to fading and interference, we usually want to have forward error correction, and you will very unlikely find a wireless system which hasn't got forward error correction. And there are two types of codes which are used, or which are also used at, for example, DVDs or any when you want to transmit or store data. And these are block codes and convolutional codes, and when you do wireless stuff, or digital wireless transmissions, they usually get combined in an inner and outer coder. The inner coder is usually the coder that's at the end of your sending part, so which is at the basically just before transmitting or before modulating the data, and the outer coder is your coder which is used after you usually randomize your bit stream. The code rate is k divided by n, which is k the number of input item or input bits, and n the number of, okay, I've got a typo here. K is the number of input bits, and n is the number of output bits. So, for example, a code rate of 1/2 means that you're actually doubling your bit rate. The simplest codes are parity check codes, and you usually do this with generator matrices. And for example, if you use add a parity bit to every byte, then you have a code rate of 8 divided by 9, for example, and the distance between the different code words used determines what your distance in error correction is. So if you use a few code words, but huge code words, then you can usually have high error correction. And an example for this is Hamming code. Reed-Solomon code is very often used, is for example firstly used at NASA Voyager missions, where it is also used with a convolutional coder, and is a non-binary code where we actually use the code words as coefficients to a finite field. And it's also used by DVBS, DVB-T, digital audio broadcasting, and ATSC, the American digital television standard. Then we have got low-density parity check codes, which are actually not new, but were forgotten for a long time, and are used, for example, at LTE and DVB-C, as far as I remember, if I remember correctly. And are basically parity checks over huge code block sizes. So you have a very large matrix, and you usually can only solve this matrix by iterating over the elements. And this is the block code or error correcting code, which is very close to the channel limit, or is the error correcting code which is which comes to the channel limit, like very close. So. Okay, to convolutional codes. These are not block codes, but are codes where we take our bit stream, our input bit stream, and convolve it mathematically. So, for example, this is a simple coder with a length of 3, or we have two elements where we save the last bit, and for every bit that comes at the input, we shift this once and do exclusive or operations on the output, and we have got two outputs, so that means that we have got a half-rate codec. And you can do this for any number of rates. For example, you can also have 4 outputs if you really want high error correcting possibilities, but means that you also have a lot of redundancy. And usually this gets used as a base code or mother code. And then we have got punctuation, which means we actually leave bits out which we don't transmit, and the receiver adds it again. So we are we are making actively errors, but we don't have to transmit the whole bit stream we generate. This is usually decoded with the Viterbi algorithm, and the reason why these codes were actually forgotten is because the Viterbi algorithm is quite complex to solve for higher length of codes. For example, DVPT uses a code length of 7, and you can, if you take this, you can actually do a state machine out of it, and you have got the states. So for two elements here, you have got 2 bits for the state. And what we are doing at the receiver side is we try to think what the sender or what the finite state machine at the sender is at the moment doing. And at this diagram, this is, for example, a 0. And if we go down, we actually transmitted a 1. So if we at first received these symbols, and then this one, we can actually recalculate the path the finite state machine that the sender was actually using. And the receiver tries to find the path with lowest distance or with lowest error. Okay. The second type of codes which are coming close to the channel limit are turbo codes. which are actually parallel concatenated convolutional codes. This is a bit of a mixture of block codes and convolutional codes. We use here, this is actually from the original paper about this. We use here 2 convolutional codes and use them as parity bits, or as we use them to add information, but we are still using the bit stream which is on the input side. And low density parity check codes are better than this, but this comes also very close. And after our forward error correction, you usually do data interleaving, because wireless channels have usually got burst errors. So you've got a small time amount where your signal to noise ratio is really bad, and you have got a lot of errors, and then you can again have a time span where you receive signals without any errors. And convolutional codes are bad at when it comes that a lot of errors are after another. So what we are doing is we are interleaving the signal, and this is the interleaver of DVBS. There are different approaches to interleavers. For example, you can have a permutation matrix like LTE has, or a convolutional interleaver where you've got these storage elements, and you with each byte you switch one of the positions. So you're actually doing like randomizing your packets over a specific span. So if you have got, for example, 10 bytes in a single row which could not be decoded, after you do the interleaving at the receiver side, these 10 bytes are spread around across the whole input stream. And then your block codes and your convolutional codes have it easier to decode them again. Then we come to channel access. The easiest channel access we have got is simplex or broadcasting, which is like every radio station does. You have got one sender, and you can have many receivers. You don't need synchronization to the sender, or you can't have any synchronization to the sender because you don't have a back channel to your sender or to your transmitter. Often this is also used if you have got, for example, a few wireless nodes which are only transmitting at a very low rate or very low time of your actually time slots. So there is no interaction between the transmitters and the receivers. Then we can have TDMA, which is time division multiple access, where we use one channel and divide it into different time spans for different senders or for different transmitters. For example, each one of these boxes is a time slot, and in each of these time spans a different transmitter sends. This is usually used, or almost always used, at mobile communications, and for example DECT, LTE, GSM, UMTS are all using this. And because we have this time splits where the second or the next transmitter has to send as fast as possible after the last one has ended, you need to have exact timings, and at wireless or at mobile communications where you have got base stations, usually base stations tell the clients when they should send. We can also have multiple channels where we send simultaneously, which is frequency division multiple access, where we have an uplink and a downlink channel, which is based by duplex offset. And both channels can be active at the same time. And if you have got good analog filtering, you can receive at the same time that you transmit. So this is actually full duplex possible over wireless. And most of the mobile networks use this. For example, if you combine this with TDMA, then the uplink channels each client gets a single single time slot, and the base station basically owns the downlink channel. And there's also cold division multiple access. If we want to transmit simultaneously, we usually need to have something that is orthogonal. For example, frequency division multiple access uses different frequencies, so we can distinguish them. At code division multiple access, we use the same frequency and we transmit at the same time. And it's only because of digital coding that we can distinguish two signals from each other. And this is, for example, used at GPS or Galileo and WCDMA and UMTS. Okay, and thanks for your attentions. Are there any questions?
Nope, I don't think so.
Okay.
Okay, so
Thanks.
I don't really know what's the next talk, so okay.
Yeah.
Sorry.
Probably most of the people in this room understand a lot of the digital end, what you explained, and the coding and the error correction. In your eyes, if you rate, well, I do not even know if this question makes sure, if you have to compare the analog or the real transmission stuff to get it to the antenna and to get it like into the air compared to the digital stuff, how would you rate it? Like the ratio is most of the work on the transmission, on the antenna, on the amplifying, on the signal processing, or is it on the digital end?
Well, this depends. This depends a lot on your signal or on your what you actually want to do. If you want to have a wireless signal, a wireless transmission, which is possible to adapt to a lot of, or if you want to have a system which can do a lot of stuff. For example, if you have a software-defined radio, you usually want to have a large bandwidth where you can choose which signal you actually want to use. Then analog stuff gets much more complicated. Also, if you have got, for example, very different very difficult. For example, mobile communications. For mobile communications, you need really good amplifiers. You need to do a lot of frequency engineering, so you can do your cell size in the right direction or in the right sizes or in the right. Yeah. Okay. I hope you.
Yes.
Okay.
Hi. Thanks for the talk. I'm a radio amateur myself, and I want to get into this stuff. What's your recommendation on free software? Do you recommend starting with GNU Radio, or is that too complex? Or what's your recommendation? Which software should I look into?
I started with GNU Radio a few years ago, and I've done a bit of GNU Radio projects. The problem, for people which are good at coding or at writing software, is that GNU Radio is mostly C++. If you really want to go into the details. If you just want to experiment with different kinds, it can get very difficult at the first. You need to get into it, so it's a very steep learning curve, but it's a very nice, it's a very nice software development kit. And also, okay. Any other questions?
No. Any other question? No. Okay. Thank you again.
Okay. Thanks.